this hour is going to be about a package called Dask. Some of you may have heard about it, some of you may not. So this is really structured as a general introduction to what Dask does, how you would use Dask with X-ray. And then if you have time at the end, I can do a demo on a supercomputing cluster that shows me using a lot of resources to do a somewhat simple problem to kind of illustrate what the possibilities are. Oops, let me just share my screen. All right, so at this point, you should be able to see that. Is the font size good?
Looks good to me. Anybody let us know if you're having problems.
Okay.
Oh, Wujong says it's too small, so maybe you can zoom in a little bit more for the projections.
Do that. How's that look?
She says one more, please. Okay.
Okay, so we're going to talk about Dask. And Dask is a way to parallelize computations that you usually do. And if you use X-ray, it makes it extra convenient because it's almost pretty transparent and pretty seamless. And so by the end of this notebook, you'll kind of hopefully appreciate that X-ray data arrays and data sets that we saw in the first lecture are Dask collections. We'll get to this, which means that you can kind of call Dask methods on them and things just work. And if you just use X-ray operations, things that we saw like group by or just addition, multiplication, all of these things, it will just use Dask under the hood if it's appropriate, and everything will just work with minor, usually very, very minor changes. So you can take a piece of code that works on your laptop and then potentially scale it up. You can either run with multiple processes or threads on your laptop, or you could do what I do at the end of this R when I run on a supercomputer, or you could be in the cloud and request resources there. So there are many possibilities. And so this is just the kind of intro to give you enough background to try something like that, if it makes sense for you. Okay, so what is Dask? And there's a bunch of stuff actually under the Dask project, but when we talk about X-ray plus Dask, we're usually talking about two things. One is the Dask array. And so this is basically a drop-in replacement for a NumPy array, which I think some of you have now worked with and what we saw in the first lecture. And the second thing is what's called a scheduler that will actually run those computations on the Dask arrays. And so we'll look at these two pieces in, well, right now, but in very brief detail. So what is a Dask array? And so the idea behind a Dask array is, we have data sets that can be terabytes and now petabytes, and it's kind of hard to analyze them because, your memory that you have access to can be a lot smaller. Though nowadays with the cloud, you can get kind of ridiculous. But for like a very concrete problem on a laptop, like this one has 16 gigabytes of RAM, but let's say I have a 500 gigabyte data set sitting on disk. How do I analyze that, right? And so there's two pieces. One is to do it in parallel, because otherwise it's just going to take a long time. So you want to use all the multiple processes or cores that you have in your laptop. And the second piece is to do it in low memory, so that you can actually do it with 16 gigabytes of RAM. You want to crunch through half a terabyte of data. That's going to require some juggling. It's possible for you to do this manually. I did a lot of that during my thesis with MATLAB, and it was very, very, very painful. I wish I had Dask back then. It would have saved my life. But Dask lets you do all these things kind of easily, and I'll demonstrate that. And so the way Dask works is, imagine this, this is nice graphics. Imagine this represents your half a terabyte array. What it does is cuts it up into multiple small pieces. Each of those pieces is a NumPy array. And so these pieces are called chunks or blocks. So these are multiple small arrays that make up your big array. And the idea is that you can take your computation and do it one small block at a time. And so, in memory at any given point of time, you just have a small multiple of these blocks running through, not the whole thing. So this is what lets you get through a giant data set in a small amount of memory. How you create a Dask array kind of looks like NumPy. So here I create a Dask array of ones. I give it a size or shape. This is 10 by 5. And I tell it chunks. So this is now 2 chunks along the first axis and then 2 chunks along the second axis. And so when you create this and you run it in your notebook, you should be able to see this. I don't know if anyone's actually doing it, but if you go to
We actually had a question, if you don't mind me interrupting real quick, that someone was asking where they can find the notebook.
Yeah, I was just going to say, so I uploaded this last night. And so you'll need to do a Git pull in your OHW tutorials. And then if you looked under Thursday, you should see X-ray and Dask sitting there.
Great, thank you.
So sorry about that. That was a little lazy. But yeah, feel free to interrupt if you have questions. So, okay, I've created a Dask array of ones. What you'll notice is you don't see ones anywhere on the screen at the moment. So the concept there is that Dask is lazy. So no ones, no memory has really been used at the moment. No ones were generated. What it does, it has a bunch of metadata. What it knows is that the shape of this array is going to be 10,5. There's something called task that we'll get to. There's 15 blocks or chunks. So, and they've been kind of schematically shown here. There's 3 by 5. And if you thought about it, so what you've said here is that there's a 5-element dimension, size 5. And you want to divide it into chunks with size 2 each, so you're going to get 3 blocks, right? So there's 2, 2, and 1. And if you go this way, you'll have 5 blocks of size 2 each, so 2, 2, 2, 2, 2. That gives you 10. So, back to this figure, what we've done is we've created an array. It's not that big, but for schematic purposes, it works. And we've divided it into 3 chunks by 5 chunks. And when Dask does, it's going to operate on a subset of this array at one given time and then crunch the whole thing. And we also talked about this, why we care about Dask arrays. It lets you use parallel resources. So you can, different cores or processes can operate on different chunks of the array at the same time. All right, so that's how you get parallelism. And because you don't have the entire data set in memory at any given time, just these little chunks, you can work with data sets that are much bigger than RAM. So people like to say Dask lets you scale from a memory-sized data set to a disk-sized data set. So your memory is something on the order of 8 to 16 gigabytes usually in RAM. But on disk, you can have like terabytes. And so this kind of bridges that gap. It lets you express your computations and do your things both in parallel, but also in low memory. And so, like I said, Dask is lazy. This is the fundamental concept, which means you don't actually get what are called concrete values until you explicitly request them. So like here, for example, I created an array, but you see, this is just a representation of creating an array. It hasn't actually been created yet. If you called mean along the last axis, you'll get another Dask array back. So you've got this nice representation again. I kill the last axis, so you're left with 10, an array of shape 10 and 5 chunks, size 2 again. But again, there are no values here. Right, and so it's pretty great that this lecture came after the bit on reproducibility, because unfortunately, this particular cell is not reproducible on your binder at the moment, because I forgot to request a package be installed. So that's a lesson. If you're interested in reproducible tutorials for a global audience, please test before you actually do it. I'm actually running on my local machine, so this should work. This won't work online, I apologize, but maybe look at my screen for a bit and then go back. So this visualize basically tells you what Dask is planning. So here's how Dask is lazy. Effectively, what it does is keeps track in like a symbolic fashion of all the operations that you're asking it to do and just stacks them on top of each other. And so at this point, I created a Dask array. You will see that down there. Maybe a little hard, firstly, but it says ones underscore like. That's creating a bunch of ones. Then I asked it to create a mean. Turns out the way it creates a mean is called something called mean chunk, and then mean ag, and then gives you an output. So this is fundamentally how Dask does it. So as you ask it to do things, it builds up a blueprint in its head of things to execute, but it will only actually execute them when you ask it to. So by default, you just have a representation of your computation. You don't actually have anything in concrete. And so how you actually get concrete values is I'm going to tell it to call .compute. So when you do this, you see, oh, now I get a bunch of values, right? The mean of ones is ones. Great. But what Dask has done is when you ask it to compute is it goes through this little graph, as it calls it, and runs each of those tasks. It does ones like, then it does mean chunk, then it does mean ag, and gives you the output, and then assembles it all together to give you back a concrete array. So this is now a NumPy array that's actually sitting in my memory and using a RAM. So I'll stop there in case anyone has any questions, but this was kind of the super brief introduction to what Dask is.
I'm not seeing any questions yet in the Slack channel. Though maybe people might still be having trouble accessing the tutorial, but I think probably that's okay since at this point, maybe it might not run on the hub and it might be easier to follow along with you.
Okay. Yeah, sorry about that.
Oh, there's a question. So sorry about that. Just came in from Adam saying, does the finished compute always need to fit into RAM? Is the workflow still RAM restricted?
The final outcome almost always has to fit in RAM. The final outcome, right? So not the initial data set, but it's sized by the final result. Yes, usually you want that. It is possible. It is possible to write to disk in parallel. So like you could add a next step to a file format at the end of this, and that would just all go onto disk streaming. And then that would not apply. I hope that answers that question.
I think so. Yeah, that seemed clear.
Okay.
Yeah, we can keep, I think maybe keep going and then we have maybe more, we'll have time for more questions later. Okay.
And so here there's a link. This is to the introductory Dask.array tutorial. So you should go through that. It's really nicely written. Actually gets to Xarray by the end. So definitely do that. This is mostly enough for you. This is how much you need to know to be dangerous with Dask and possibly bring down your computer. So next we'll talk about Dask plus Xarray, right? So let's remember the key concept I was trying to push in my first lecture was that what Xarray adds is the ability to use metadata to express your analysis. And in that lecture, we just saw it wrapping NumPy arrays. So these are arrays that live in memory. And so that's how Dask plus Xarray fits in, is instead of wrapping a NumPy array, you map one of these Dask.array things underneath. So that's how, conceptually it fits in. The way this works is first I'm going to import Xarray. It's going to take a bit. And so usually, at least in that data set, in that lecture, I opened tutorial.openDataset at temperature. And so when you do this, you get a little thing. There's some details here, but basically this is not a Dask array. It's a bunch of values. It hasn't actually been loaded into memory yet, but it's not Dask array at this point. And so usually when it comes to all these different array types, what's important is how to create them. And so Xarray lets you do that. So to create a Dask array, you pass this chunks argument. So remember, chunks tell you how to cut up an array along different axes. And so here I know that this is a 3D array. There's time, lat, and lon. So I'm going to tell Xarray, hey, open this up as a Dask array. But when you do that, make sure you set these chunk sizes. So 25 elements along lat, 25 along lon, and -1 just means all of time. All right. And so let me show you DS. So you run this where you get up. Oops, sorry. Here's data set. Here are our 3 coordinates. Here's a data variable air. If you click that database thing, you'll get the Dask representation that you should be familiar with now. So you can see this is not that big. It's an example data set. It's 15 megabytes. It's got the shape and it's taken these chunk sizes that I asked it to. So in this case, I chose to chunk all of time along one axis, as one chunk. So there you go. Now you have an Xarray data set that's wrapped, that has a data array called air that wraps a Dask array. All right. And so if you look at ds.air.chunks, this is kind of a Dask array property. It tells you that there's 2920 along time. So that's all the time axis. It's 25 along latitude. And then on longitude, there's a 25 size chunk, a 25 size chunk, and then a 3 size chunk. So that's how you create a Dask array. Is usually you give it this chunks argument when you read in your data. And when you do it that way, all of your variables will end up having the same chunk sizes. This is not a requirement. You can create, read a variable from a different data set with different chunking and then combine all of that together in a single data set, and it's all fine. So just for awareness, not really important at this point. Okay, and so, right, we specify chunks.
Can I interrupt with maybe one question that looks like a few people were wondering about the chunk and the size of the chunk? Do you have to choose that based on your own RAM limitations?
Yeah, so this is kind of interesting, and it's a big trade-off and like a real source of troubles. Usually, the recommendation is to look for something like 100 to 200 megabytes. There is a Dask array best practices somewhere. Yeah, you can see, I look at it all the time. So yeah, you can see it right there. Select a good chunk size. So it is rare to see chunk sizes below 100 megabytes in size. So usually that's like a good rule of thumb. It really depends on what kind of computation you're doing, what you're doing. And again, as you mentioned, what resources you have. Sometimes I'll bump it up depending on what I'm trying to do. There's a trade-off between chunks. So that's basically how many pieces you cut your array into. And this other thing that is tasks, which is how many tasks do you have to run through. And once you get to complicated stuff, you can see this getting into now like millions and millions of tasks, which when it can be kind of problematic to like actually do all of that. So there's a trade-off there between cutting your array into many pieces and the increase in tasks that happens when you do that. But 100 megabytes is like the rule of thumb. You don't want it to be too small, you don't want it to be too big.
And then maybe quickly following up on that, can you do the chunking in an optimal way for reading data sequentially from the hard drive? Or yeah, that's the question.
If I understand, the question is really, can you match the chunk sizes to chunk size on disk? Because files tend to have chunk sizes, is that right?
Something like that. Instead of it being somewhat arbitrary prescribed by the user.
Yeah, so usually it's somewhat arbitrary. You can have it match whatever is stored on files. So technically NetCDF4 files are stored as chunks, but those chunk sizes end up being small. They end up being like 1 or 2 megabytes, which is really too small for Dask. And so the other way to phrase your question is it is usually possible to have Dask choose a multiple of the chunk sizes on disk. So it gets that optimization that you're asking for, but also gets it big enough that you don't have too many tasks. I think the answer is to put like auto here, but I don't know if that really works so well with this data set. It's just so small anyway. But you could look up this chunks equals auto thing that tries to match what's on disk.
Great, thanks.
Okay, so moving forward. So we have this little data array. And like I said, sometimes we want the underlying values as a concrete array. So there are a couple of interesting things. One is there's the .data property we saw in the first lecture. So this is a Dask array, .numpy. And sometimes you do want to convert it or like actually compute it. So usually I'd recommend you do as NumPy. So when you do this, it actually loads data into memory. So you can see a bunch of values there. If you extract the data of this thing, this is also a bunch of values. So this is a NumPy array. So there you go. This is how, given a Dask array, but you actually wanted some concrete values to look at or to plot, you should be using as NumPy to do that. Or if you just wanted the underlying array, use .data, which is what we saw in the first lecture. So yeah, this is an exercise. I don't know how many people are following along, but I'll wait 2 minutes in case someone has questions too, but just try mean.data, try mean.values. Mean.values is really a synonym for ds.out2 numpy. It's kind of an older version.
I don't see any questions, new questions necessarily coming in, but we did kind of have one question about is it right to think of Dask as sort of fractioning our calculation process, sort of?
Yes.
Yeah, okay. Great.
Yes, it does small pieces at a time and then combines it all together to get the final value. That's exactly it.
Great, thank you. Thanks.
Okay, and so the other concept, remember, is that Dask is lazy, which is What we mean by that is that when you ask it to take a mean, it doesn't actually take a mean. It just says, okay, I need to take a mean at this point in time, at this point in the calculation, but it doesn't actually do it. The same thing happens with X array. So ds.add, remember, is a Dask array. So if we call mean of time, we get back an array that is latitude by longitude. Makes sense. We kill the time axis, but it's still a Dask array. It hasn't actually been computed. This will be the output chunking and all that. Dask has figured that out for you. Here's all that X-ray metadata we like, and it's all there. And so yeah, Dask is lazy. So an X-ray thing that wraps a Dask thing is also lazy. Like at this point, we don't have any concrete values. As I mentioned earlier, Dask is constructing this graph like a representation of all your calculation in little pieces. And then when you ask it to compute, it will actually do all of that for you at one go. So this is just kind of emphasizing that point. If you looked at .data, you will get a Dask array because that's what it's wrapping. We can visualize this graph. Again, unfortunately, this won't work on the binder, but this you can look at my screen right now. And so what this is saying, this is that symbolic representation of your calculation. This big square here on the left is a file. There are 3 open data set calls. So it's going to open up, read one chunk, then the second chunk, then the third chunk. Then it's going to calculate. It's going to try to calculate the mean chunk-wise. Sorry, one second. Sorry about that. So what it's going to do is the end is going to be the mean, but it's taken the mean calculation and broken up into 2 steps. One it's calling a chunk step, one is calling an aggregate step. Details don't matter, but this is, come back to that question about fractioning your calculation. This is how it's doing it in parts. It's going to calculate enough information to get the mean at the end at this point, and it's going to do another step, and then it's going to give you the final value. And so usually you can keep like building this graph up and up and up, get a large number of tasks, and then you execute the whole thing at one go, and it just goes through and streams through the whole calculation. All right, and so, like I said, at this point, we just have an abstract representation. Sometimes you actually do want to know what the mean is. And so the way to do that is you call mean.compute. And when you call .compute, it will run the calculation and give you back another X-array thing. Remember, mean was an X-array thing, so you get back an X-array thing, except now mean is wrapping a little NumPy array with actual values here. So here, just to illustrate that, here's mean. It's a Dask array. Here's mean.compute. It's got actual values. So it's run through that calculation. It's gone through this graph from left to right and given you the output, which are these last few cells, is 3 blocks. So yeah, so .compute is how you usually get a thing, a kind of concrete value thing. A shortcut is calling .load. So this replaces it. So this is equivalent to saying ds equals ds.compute. So, here I did mean.compute. And so game showed me some values on screen, but the actual mean object, like right now, as we run this again, and it's still a Dask array. So the actual original object was not changed. When you call mean.load, which is what this exercise goes through, you'll get something else. So I'll wait for anyone who's following along if there are questions.
We did have one question in the chat that came up, which was if you ask X-array to compute a mean over an array that is larger than the available RAM, how is it doing that? Or would it do it in chunks in a similar way to how Dask is doing it, or would it simply not work? So I think if I understand the question, it's, like
yes.
Yeah.
So what X-array is doing is it's telling the Dask array to compute its mean for itself. So it's delegating out to Dask. So it uses all of the Dask magic under the hood. So that's why we started off with the introduction to a plain Dask array, because all of those concepts carry over to X-array. Because all X-array does is wrap things. And when you tell X-array, hey, give me the mean, X-array in turn will go down and say, hey, you array, give me your mean. And so that will do the appropriate thing depending on what array you have. That's how that's working. So this is what we mean by it being like pretty seamless. Like you can write code that works with your tiny data set, and then you can move to this bigger data set, and it will mostly just work as long. You may have to tweak things like chunks and resources and all that, but there's a good chance it will just work.
Awesome, thanks.
So yeah, here I'm going to shoot data.load, mean.load. And then when we examine mean after this, you will find that it now has a NumPy array. So this is commonly you'll find yourself either calling .compute or .load, because you construct a big calculation. Usually you're reducing down to a much smaller array. Like this thing is just 25 by 53, very comfortably fits in memory. So then you call compute at that point, and then you do whatever you want after that, like make a figure or something. All right, so when you've been saying .compute and .load, Dask has actually been running in parallel. It hides this detail from you. It spins up two little threads usually. Details don't matter. Basically, it's hidden behind you, and it was actually trying to do it in parallel, even though you couldn't see it. When you start to get to much bigger resources, usually you'll want to set up what's called a distributed cluster. The good news is you can actually do this on your laptop or on that binder, and it should just work. And it's called what's called a local cluster. And so we're going to do that. For me to run locally, I'm going to want to change this. But basically, you call it from Dask.distributed, import client, and then you call client. When you run this, it will start spinning up some resources. You should get this nice little wrapper. You click cluster info. So here's on my laptop, it's given me 4 workers. Each of these is running 2 threads, and total memory 16 kilobytes. There are like lots of details you can get into about parallel resources, but for the purpose of this lecture, I've now told Dask, hey, go ahead, use all the cores and all the memory that I have. You can customize this, I can do it, and we'll use that to run our computations. The cool thing about using this distributed package is if you go to the left of your screen, you should see this icon, and then hit this, oops, this little search bar. Oh no, it's not working. So if you click that URL, it should work. You should get a little status screen. I'm really confused about why. Oh, yeah, I'm a little confused about why that wouldn't work. It should hopefully work on your binder. I checked it before this lecture. But what this is a bunch of diagnostics that lets you look at your parallel computation and your resources. So what I'm going to click, you can explore this for a while, but a couple of things are usually useful are what's called progress and task stream. And this stuff is really fun to look at. There's a lot more stuff you can get into, but I'm not going to do it right now. So basically, this is a dashboard that's a view into the computation as it's happening. So as someone pointed out, we're kind of fractioning our computation, and you can see Dask do that. So here's a little tiny test little thing. It just creates a number of ones, and it computes them. When you do that, you should see stuff happening out here. You see there were 2,000 ones-like tasks, and they got run in series. So each of these, you can zoom in. So that was a little task that ran for 140 microseconds. And then it ran the next task that was probably another 140 microseconds. So this is how Dask works, right? This is each little piece of your compute happening in parallel, and then each thread is running it sequentially. So yeah, hopefully this is working on your binder. I tested it before I did this, so hopefully that's all happening. And so now I'm just going to illustrate some kind of computation. Here's your ds.air again. I selected out a tiny piece. You still get back a Dask array. Xarray works very, very hard to not call compute for you. It will try to give you a Dask array back basically all the time. And so that really means that it's up to you to choose the right point to compute something. So this way, you can set up your computation. You can make sure you have all the resources you need before you actually run it. Yeah. So to just illustrate that, here's a bunch of stuff. Here's a time rolling mean, 5-point running mean of your time series, a long time, comes back as a Dask array, which is pretty sweet. You can just keep going. Here I extracted one little time series. And now I'm going to compute, right? So I'm going to call compute here on the entire rolling mean. And you should look to the right side of my screen, or if you're following along and running it, you should look to the right side of your screen. And you should start to see all of these little tasks, right? Well, it was very quick. This is pretty small. But basically, here are a bunch of concrete values that came out. And it came out in compute. And if you zoomed in here, here's the record of the computation that it ran. It was kind of small, so it didn't really have much to do. But as someone said, what it's done is taken that computation and broken it up in little pieces, and then figures out how to run those pieces in parallel to get the answer that you want. So here's like a little divide that happened for some reason by the end. I think that's for the mean. You divide the sum by the count to get the mean. So that's that divide at the end. Okay. Right, so that was computed. This is just back to that same concept where, because I called compute and then assign it back to the same thing, you still have a little Dask array as that rolling mean. So I'll kind of stop there. So the idea of this lecture was just to give this basic idea that there's this package called Dask. It lets you scale to problems that are bigger than the amount of RAM that you have. You can wrap those Dask arrays in X array. You can usually do that by employing this chunks equals argument when you read in your data set. And you can basically line up all the computations that you want. Any method that's in X array, like this running mean or group bys and stuff, are all pretty Dask aware. So you will get back a Dask array, and it's up to you to call compute, which is what we did here. And when you do that compute, assuming you have this cool dashboard setup, you should be able to monitor your computation. You can check how much memory, how much CPU it's using, and all of that. And the other really core idea is at this moment, like I'm running on my little local computer. You are running on a little binder hub, but it all mostly looks the same. If we have 10 minutes, I'm going to switch to a different notebook that's running on my supercomputer cluster, and I'll show you that, and you'll notice that it also looks basically the same. The only difference in all of these places is how you ask for resources. So I'll get into that a little more. But are there any questions at this point?
I don't see any more questions that have come in on Slack, but I actually have one quick question, which is I'm wondering if you have any tips or resources for doing, or yeah, even if it's a good idea to do more complicated things within Dask, like for example, SciPy, like I've been trying to use SciPy optimization routines parallel, and you know, I'm curious about more complicated computations.
Yeah, good question. I don't actually show it here, but I'll get to your question. The first thing is I'm going to finish. I finished up this notebook, so I'm going to hit client.close. What this does is releases all the resources back. So if you're in the cloud, you don't get charged. If you're on a supercomputer, also I don't get charged. And then back to Allison's question. First bit is that we have a little bit in our user guide about Dask, so that's one thing to read through if you're useful. It's very useful. So like, yeah, it shows you how to read with chunks. There's a bunch of stuff. We scroll down, there's this bit that's called automatic parallelization with apply ufunc. This is a very complicated topic. If you're going to do this, I recommend you go to the XOA tutorial website and you scroll down here to parallelizing custom functions. This material could be a lot better, but it's there and it tries to build up applying very random SciPy functions to Dask and how to think about that. So I would recommend you go through there and then ask for help if you need it. But this is where to start. Go to the XOA tutorial website and look for parallelizing custom functions.
Great, thank you.
Yeah, it's a good question. All right, so if there's no more for the last 10 minutes, I've switched to here where you see up here is jupyterhub.hpc.ucar.edu. This is very similar to what you're seeing on Binder, but now it's running on NCAR's supercomputing system. I'm going to bump up my font size again, as requested. And so this is really, it's actually not as, okay, it's a bigger problem, but it's not as big a problem as I was hoping because I ran out of time. But what I'm going to just do here for demonstration purposes is to read in a 60-year global simulation. It's nominally 1 degree. Indicator is kind of half degree. With daily mean surface output. So for 60 years, it runs from 1958 to 2016, actually. So it's maybe 58 years. And I'm just going to show you how to calculate composite mean SST anomaly for non-linear and nonlinear phases. The anomaly is defined with respect to the neutral phase. Kind of doesn't matter. What really matters is I want to show you how this kind of scaling works in practice for like a problem. This is the data set I'm looking at right now. So I have a bunch of imports, kind of doesn't matter. I'm just going to run it. And remember, so this is where this question about resources comes from, right? So when you were running in that previous notebook, you saw a thing called local cluster that runs on your little machine that you have access to that you're like typing on, and it works pretty well. It could also run on that binder pretty well. You just have access to all the stuff that you asked for when you logged in. I'm on a supercomputer right now, which means I have access. I'm super privileged and I have access to a lot of resources potentially. And the way you do that is you submit jobs to a queue. On this little terminal here, but it's kind of a mess, is basically monitoring jobs that are submitted with my username to the queue HTC. You see one job running right now. That's one that's showing you this window here. I'm gonna make my screen bigger. And so you were running local cluster. We use a software called PBS to run the queue for the supercomputer. So here's a thing called PBS cluster. It comes from this package called Dask job queue, but it sets up things for distributed, right? And it's maintained by a bunch of people that tend to work on supercomputers. Here are parameters for resources that I'm asking. I say I want each Dask worker is going to be 1 core, 23 gigabytes of memory per one process. Queue is Casper. Some of these are kind of local details on how you specify things. Here's the project that the compute time gets built to. Here's how much time I asked for. Here's the network interface. There are some details here. It really depends on if you worked with a supercomputer and like submitted jobs through PBS, some of this will look familiar. If not, don't worry. This is just a piece of code you need to run to get the resources on this little machine. So you're going to create this cluster, and then I'm going to say adapt, which is minimum jobs 2, maximum jobs 12. So this shows you scaling. What it's going to do is eventually you should see it show up there. If it works. I'm going to connect a little client to that cluster. Here you go. You see it's requested 2 jobs in my name. It's called Dask worker. And they asked for 23 gigabytes of memory. You'll see eventually it'll start running. So I've created a client. I'm going to do the same thing when I hit this. And I already set this up to kind of save some time. Yeah, the font size is messing it up. So I'm going to exit the terminal at the moment. Just understand that in the background, Dask has requested resources from the queue for me. Here you'll see these are workers. There are 2 of them at the moment. And yeah, we can talk about this if people have questions. The really high zoom here is kind of messing things up. But anyway, so I've requested Dask has started 2 jobs for me because I said minimum, I said maximum 12. So when I actually compute, you'll see it scale up and request more. Moving on, so I've requested parallel resources. Next step, remember, is to read in the data set. Here's a bunch of mess. This is the path to a bunch of output. There's a bunch of grid info. What I'm going to do is I'm going to do parallel equals true. This reads a collection of netcdf4 files. It's got a bunch of surface variables that are daily means. And because there are about, I don't know, thousands of files, I'm going to ask it to read in parallel, because otherwise it's just going to take like a minute. And so let's do this. You should see it show up here. There are 708 files, so 708 open data set tasks. Dask is running them. Should show 2. Oh, now you can see there's 4, 5. You can see it's scaling up, right? We started with 2 workers. Oh, hard to see with the zoom. Here's now we have 6. So that's that little adapt line. That's what that does. Is depending on how much work it has to do, it will keep asking for more or scale down depending on what you're doing. Again, details, I'm happy to talk about it, but this is mostly as a demo. Here I use this parallel true to parallelize reading 700 files. Otherwise, it would take a while to do that in serial. When you do that, you look at this SFC thing. It's going to be a little X-array data set that has a bunch of surface variables that were stored in those files. So this little, I forgot to mention, I used OpenMF dataset. That is multi-file dataset because it's so common, at least in our field, to have collections of netcdf4 files, like 1 per time step or something saved. So this kind of makes it easy for you to read something like that really quickly and in parallel with Dask. So a bunch of magic that happens under there, but most of the time you don't have to know about it. It just works. So here's my little dataset, SFC. It's got a bunch of dimensions. There are 26 coordinate variables. So here are a bunch of dimension variables. There's geo, lat, and lon. This is the grid info, like area cell O is the grid cell area, and a bunch of stuff. You have a bunch of data variables. Here's SSH, TOS. If you look at the attributes, turns out to be sea surface temperature. That will be sea surface salinity, SOS, and then sea surface U and V, and a bunch of other stuff, right? So basically with this one, kind of longish line, it just went through, ran 700 files, assembled them all up in memory. So it's concatenated them a long time. So there are 21,000 time steps, daily time steps, and 16 different variables, right? All of this assembled together into one thing that you can then manipulate to do what you want. I'm going to pull out the sea surface temperature. This is showing off that CFX array package I showed you earlier. I ask it to find the variable with standard name C_surface temperature. It gives me back that variable. Turns out it was called TOS. A detail you didn't need to know because it looked at this attribute that was present, the standard name, which is very nice. As you can see, this is a little Dask array. My chunk size is a little bit on the small side. These are kind of smallish data sets, so it's only 20 gigabytes, but it's a lot of time steps. And chunk size is about 30 MB, is a little small. Ideally, I'd go bigger. This is the problem I constructed. What you're going to do is, remember, we wanted to get to some kind of El Nino composite. So the first thing to do is to calculate what's called mean SST in the Nino 3.4 region. That's defined like this: 5 south to 5 north, 170 to 120. So I take my SST, and then I say, hey, select along the latitude axis from 5 south to 5 north and 170 west to 120 east. Again, I'm using that CFX array to express this in very general terms. This will go in and figure out what the latitude axis is for you and the longitude dimension. Then I'm going to say, take a weight by the cell area, which is some information that's present, and take the mean along X and Y, which would be latitude and longitude. So that gives you the correct area average mean in that region. But then remember, I had a daily time series. So this is resampled to monthly. Yeah, let me actually do this from here. So the subset to Nino region. Then we take the proper weighted average mean SST in that box. And then I'm resampling to monthly. And so you do the mean when you're doing that resample. And then here at the end, I call load. All right, so I set up a bunch of operations. It's all pretty abstract, and maybe I'll demonstrate that. So we just did all this. We will think about it, construct a little graph, and probably just give us a little Dask array. There you go. You thought about it for a while, you end up with a time series that's 708. That's right. I took the mean along X and Y, so I just expect a time series that's monthly mean. You got all the right time vector on the x-axis, and it's all good. So at this point, I've set up that calculation. I'm just going to call .load. Remember, this is going to compute, so let's look at the right. So here you go. Here are all the steps that it's running and scaling up slowly. The one thing that is useful to look at is cluster memory, since that came up. So if you note here, I've requested a couple of resources. It's 256 gigabytes. I didn't really need it. As you can see, it's using like a pretty small amount at this point, 2 gigabytes. So this is part of that Dask thing, right? This is a 20 gigabyte data set that is crunching through. It's really only using 2 gigabytes at any given point in time in your lab. So, I have access to a lot of stuff, but it didn't actually need it for this problem. So there's some level of tweaking you can do depending on the problem you have, what you want. So anyway, so this is computing, it's doing a bunch of things. In this next line, what I do is calculate the Oceanic Medial index. I don't want to go into details, but we can do that. We can plot it. And that's the metric I'll use to decide what's La Nina and what's El Nino. Yeah, so here's a nice little plot of the monthly mean SST. So that's the time series, time on the x-axis, SST on the y-axis. You see those nice labels we saw in the first one. This is using a little extension called HVplot. It gives you nice interactive figures. I don't know if you've seen this. I think you may have, but you can kind of zoom in. This is the Oceanic Medial index, so you can kind of zoom in and see. Let's see. I think you could see that's the 97, 98 El Nino, where you have really high ONI. No, we wanted compositing, so just, this is really a demo. I can share this notebook if anyone's interested. I'm going to create a time series called ENSO phase. By default, it's neutral, where the ONI is greater than 0.5, I'm going to call it El Nino, where it's less than negative 0.5, I'm going to call it La Nina. This is kind of an easy way, just for demonstration. So you see that little time series now has El Nino and La Nina in hopefully the right places. I'm going to assign it back to SST. Make sure I moved back from a monthly frequency to a daily frequency because that's what my SST is at. And then compositing, you should think of that as a group by operation. So what this is going to do is I'm going to group by 3 groups with labels El Nino, La Nina, and neutral. And then the composite is really group by dot mean. So what this will do is it will take every time step labeled as El Nino along that vector and compute the mean of that, give you one value for El Nino, then it'll give you one for La Nina and one for neutral. And so if you look at this composite thing, you should see again, remember, you've used X-array operations, so it's all Daskified by default. So that's a Dask array. It's got all that useful metadata. You've taken the time axis and compressed it down to just 3 elements, which is basically the mean for each of those El Nino phases, El Nino, La Nina, and neutral. And you have a Dask array at this point, but we actually want to look at it. So let's call .load again. So now if you go back here, you'll see it's set up that compute. And it's going through again in parallel with all these resources I've asked for. But again, keep an eye on here. It's going to go up some. But hopefully it won't be hitting 20 gigabytes, which is the size of the input data array. So this is, yeah, it will take a little bit. Are there any questions? Or
we did have one question in the Slack, and also I want to be a little bit mindful of the time because I think we are at the top of the hour. But yeah, the question in Slack was, have you tried Curd Chunk on HPC?
Ooh, I have not. I want to, but I have not at the moment. That would help parallelize the read, and that would help do the read and the video better in theory. It's my understanding, but I haven't tried it. So yeah, I mean, we could stop here. So what I do is I calculate the anomaly like that, and then I make this nice plot that's actually already up here. You can see that in El Nino, the tropical Pacific is 1, and La Nina, tropical Pacific is cold. So pretty simple, but we've parallelized that. It was only a 20 gigabyte data set, but we used a third of that in memory. Oh, here it is. There. So yeah.
Awesome.
I think I'll stop there. Yeah, it's good.
Great. Well, thanks so much, Deepak. And I'm sure if people have more questions, they can reach out to you on Slack, hopefully, and also check out the resources online. So I think I will stop the recording.